Thank you, Serena, for the introduction, and thanks the organizers for inviting me. I really appreciated that. And okay, so today I will talk about something that actually is more harmonic maps, let's say harmonic maps related rather than free boundary. Okay, but I tried to make the topic as free boundary as I could. Okay, and actually it's interesting. I will sketch the why at the blackboard if I have time at the end, but. I ended up thinking about this problem with my two friends, Mattia Freguglia and Nicola Picenni, coming from a different paper that we have that is on a notion of fractional perimeter in codimension 2, let's say. And in trying to do something for that notion of fractional perimeter in codimension 2, we had to address the problem that I will speak about today. Okay. Let me start my... Okay, so today we always talk about Sobolev maps that go from an n-dimensional domain to a sphere, okay, to a k-dimensional sphere. So you can imagine that U has k components, so it goes in Rk and has modulus 1 almost everywhere, okay? And in particular, we are interested in the limit as P, the exponent of the space, tends to k, which is the... Okay, this first. So here, what you have to think is the following. If you imagine a standard vortex, so for me, n minus k is the dimension of the singular set, okay, of the map, and k is the codimension of the singular set. But I will draw examples and a lot of pictures during the talk, so I think that you can disregard this for now. And note that p equals k, so let's say, the dimension of the Rn these spheres sits in, is the first exponent such that the standard vortex with components in these Rk and then just invariant in the n minus k directions is not in W1k, okay, around the subspace. So this is just is the same that x over mod x in R2 is not in W12. Okay, so I am approaching the first exponent where the singularities of the top stratum are not in the energy space. Okay, so the first reduction is everything I will say about our results holds for any codimension. Okay, so for the dimension of the spheres in the target arbitrary, but I will focus for k equals 2 because I think it's so first I will just draw pictures for k equals 2. So and I think it's very reasonable just to think about codimension 2, so the first codimension after codimension 1. Okay. So a model example to keep in mind is the following. So is an n minus 2 dimensional object, the singular set of U in Rn. So for example, let me draw. I will refer to this picture more than once during the talk. So picture 1 is, okay, let me draw first. N equals 2 is, as I said, U of x equals x over mod x from R2 to S1. And this is a map with a point singularity at the origin. Okay, a point vortex at the origin. And the second example is n equals 3. And the model is that U has a singularity on a curve, so a one-dimensional object. So you can imagine that I have a closed curve in R3, gamma in R3. I call it sigma, yeah, whatever. Sigma in R3. And my map, U, you can think the map as from the exterior of the curve to S1, and is smooth, okay, and has degree plus or minus 1 on small circles that go around the curve. Okay, so the map is smooth. Actually, it's not super trivial, at least for me it wasn't when I first saw this, that for every closed curve in R3 such a map exists. This needs to, it means that the map is always, the curve is always a boundary. Any closed curve in R3 is always a boundary, okay. And really what you have to think is that your map is more or less constant, let's say, outside the big compact set that contains the curve. And as you approach the small planes orthogonal to the curve, you see a point singularity like in R2. Okay, so this is the model example to keep in mind. Okay, now to state the kind of results we will be interested in, I will often prescribe boundary conditions. Okay, so consider omega a subset of R3 and fix a map on the boundary with some point vortices. And with this, I mean with, so the boundary of omega is two-dimensional. And so I just put some point vortices of this type on the boundary. So if you want, so this is omega, a subset of R3. And on the boundary, I put some vortices, plus, minus. And these are locally of this type, okay? Then consider the W1P energy for P less than 2, okay? So now, since I fixed K equals 2, P will tend to 2, okay, in my talk. And just minimize the P energy for among all the W1P maps that agree with G at the boundary. Okay. We call such U a P energy minimizing map. This is like a regularized version of harmonic maps. And why I will speak about this later, the link with harmonic maps. So the objective of my talk today is to make the following idea precise, so that if you take this picture, so omega with fixed boundary condition, that for P very close to 2, this renormalized energy, so 2 minus P times the gradient of U to the P, is close to the total length of the optimal connection between the vortices of G. This means the following, that if I have a domain in R3, and I look at the singular set of the P minimizing map, okay, I would expect the singular set to do something like this. So what I'm saying is that the minimal energy P harmonic extension will tend to have the singular set that is a sort of a minimizing minimal surface with prescribed boundary datum, okay? So this will need some machinery to make precise, and there is a catch in some sense in this picture, but this is this kind of plateau style motivation for the problem is one of the central, let's say, questions that I want to address in my talk. A second related motivation is the one coming from the theory of harmonic maps. That is, one would like very often to consider harmonic maps with prescribed boundary datum, or in a closed manifold in a prescribed homology class or something like that. But very often, the space W12 with prescribed boundary datum can be empty. Okay, there are very simple examples for this. Is I think is the most simple example with prescribed boundary datum. If I consider the W12 maps from a two-dimensional disk, so I consider maps from a two-dimensional disk in R2, that on the boundary they are X over mod X, okay? And then try to find a W12 extension, then this results in the empty set. Because if a W12, I mean, there are many ways to see this, but if the W1 is, if such an extension exists, then I minimize the energy among all maps in W12 that do this, and I get a weakly harmonic map with values in S1, but in 2 dimensions, weakly harmonic map are smooth, and so this would be a smooth extension of the identity on the boundary of the disk to the interior, and this does not exist. Okay, so, and this goes to the second motivation of the, let's say, of relaxing the energy, is that one would like nevertheless to identify, let's say, canonical maps that are morally harmonic even without being in the energy space W12. Okay, so one would like to identify these maps usually as limits of some relaxed functional that are, and with Moriel harmonic, I mean that they will be really harmonic in most of the places, but they will develop singularities. I mean, in any way you relax that problem, when you converge to a map that is in W12 or whatever, you will have singularities, right? Because I just proved in words that you cannot have a W12 extension, okay? But then you need a notion of convergence that allows you to keep the singularities and to keep track on where they are, if they minimize some sort of renormalized energy, etc. Okay. So the first idea to address this problem is the topic of my talk. So is to slightly relax the energy space. Okay. So instead of considering the W12 energy, one can consider the W1P energy from P less than 2, minimize, and then study the step of what do these maps UP, what does this map UP do as P tends to 2? Okay. And this is the step we will be interested mostly today. Okay. So there is a vast literature on this problem at this point that is mostly for the case of minimizers. So you prescribe the boundary datum, you minimize, and then you study the limit of these maps in some topology as P step to 2, okay, by many people, Hardt, Lin, Coron, Gulliver, Chen, Wang, and many other people, okay. I think that at some point between the 90s and the early 2000s, it was a very, I mean, many people were working on these problems. Nowadays, not so much. Okay, so first, an observation, which is, so since n minus 2 dimensional singularities, so singularities of codimension 2 of this type, a curve in R3, okay, cost infinite energy in the limit space, in the limit problem. So it is reasonable to expect that the singular set of U will try to be as minimal as possible in a suitable class, right? Even if I renormalize the energy, still these singularities cost an order of magnitude more than how much the map pays outside. Okay, so if I take a set compactly contained outside the curve, in R3 minus the curve, so it is reasonable to expect that here, for example, the maps will converge in W12 to a map that is W12 and is even smooth. Okay, but on the curve, you will pay infinite energy, and this is why you need to renormalize. And so all the energy that is paid more or less by the length of this. Okay, this is why one expects this that this also models the area in some sense. It's a diffuse model for minimal surfaces. So this is a rephrasing of the plateau style motivation. This one. So the fact that these maps, the minimizing maps with prescribed boundary datum, will try to connect the vortices with the least areas possible. So the second idea to address the problem that in some cases no W12 map exists in the space of competitors is to relax the constraint that the modulus of U is 1. Okay, this brings to a very well-studied topic to this day, which is the Ginzburg-Landau type approximation, which is essentially is the following idea. Instead of considering maps with values in S1, you allow the maps to have values in R2, okay? And you minimize the Dirichlet energy plus a penalization term that when epsilon goes to 0 will force your maps to have modulus 1 almost everywhere. Okay. This is the codimension 2 analog of the Allen-Kahn functional or Kahn-Hilliard functional. Now, there are reasons for which this analogy is very misleading. So for the point of view of the analysis, the analog of the Allen-Kahn functional is not the Ginzburg-Landau functional, but is the Yang-Mills-Higgs functional, and I will talk a bit about this later, and I can tell you more if you are interested. But this functional, even if it looks exactly the same as Allen-Kahn, it behaves very differently. Also, the energy is paid, in some sense, not on the singular set, but only outside, and this makes a mess. But we will talk about this functional later. And so the idea for the Ginzburg-Landau approximation is take this functional, minimize among all W12 maps with values in R2, right? Take a minimizer and then send epsilon to 0 to recover a map that is sort of harmonic and satisfies that the modulus is 1. Okay. Okay. Also on this problem, there is a vast literature. Again, this was very popular at the beginning of the 2000s. There were great works by many people: Betuel, Brezis, Hélène, Orlandi, Lin, Chen, Stuve, Tristan Rivière, Robert Gerard, Sonner, Sandier, Serfati, and many other people. Okay. So I want to give you an idea what kind of statement is like a convergence statement for the mass for Ginzburg-Landau. Okay, so I just picked some random, very reasonable things that you can take from the union of all these works to present, okay, now let's take a minimizer of Ginzburg-Landau, send epsilon to 0. What is the limit? Okay, so let's say we minimize the epsilon version of the Ginzburg-Landau energy with prescribed boundary datum in W12 with values in R2. Okay. Then, if you send epsilon to 0, more or less the following happens. So first, the maps converge to a limit map in W11 from omega to R2, where the modulus is 1 almost everywhere. Not, okay, maybe there are results. The convergence is a bit better. It converges W1 every W1p for p less than n over n minus 1, whatever. The thing that is important is that it does not converge in W12, right? Because it would create a map that does this. Okay. You converge in a weaker space. The limit is distributionally harmonic in a suitable sense. I don't want to go into the details of this, but you can think that U0, so the limit, satisfies a condition that if you know that U0 is smooth, it means that you are an harmonic map, okay, with values in S1. But it's not exactly the same PDE. It's like the same PDE, but a bit different. Okay, then the n-2 Hausdorff dimension of the singular set is finite. This is what one would expect from a codimension 2 model, right? Like this of the curve NR3. And the singular set is n-2 rectifiable. Outside the singular set, U0 is a smooth harmonic map with values in S1. So you really have recovered an harmonic map in a lot of places, unless this rectifiable set is super wide, but okay. But to talk about these results, so our version of these results and let's say, the result that I presented here is more about the convergence of the maps. For us, both my paper with Mattia and Nicola, and in general we present other known results, we will be more interested in the convergence of the singular set. Okay, so really in recovering area minimizing currents with this model. Okay. To talk about this, I need some basic terminology on currents, and I will be very sloppy on this because I don't think it's too important. So just to fix the notation, I will call DMC the space of smooth M forms with compact support. Okay. Then for us today, an integral M current will be an element of the dual of the M forms, so a guy on which you can integrate M forms. Of this form is an M rectifiable set, so you have Lipschitz charts, if you want, an integer multiplicity and an orientation, okay? So I will never speak about general current, so I don't see the point in presenting general current. Okay, so for us, an integral M current will always be an object of this type. the mass of a T as above is just the weighted HM measure with respect to its multiplicity, I mean, restricted to an omega. Okay, this is the, no. And for a current as above, okay, so also the boundary is the boundary, right? So I have defined a current as a rectifiable set with the multiplicity and orientation, and the boundary is the boundary of everything, right? So the boundary of the set, the orientation induced at the boundary, and the multiplicity at the boundary, okay? And for a T as above with no boundary, so if I consider a current with no boundary, I will call F the flat norm of T, which is the minimal mass among all the n+1 dimensional fillings of the current. Okay, this is the minimal plateau filling. So if I have a curve gamma in R3, as before, the flat norm is trying to infimize among all the two-dimensional surfaces sigma such that the boundary of sigma 2 is gamma. Okay. Giving the minimal plateau filling of that curve. Okay, I will need another notion to speak about these results on the convergence of the singular sets. That is the notion of the Jacobian. So just for mass with values in S1, in the one-dimensional sphere. So if I take a map in W11 from omega to S1, okay, we can define what is called the pre-Jacobian or whatever, the pullback of the volume form on the circle. Okay, so d theta is the volume form of the circle, and I just pull it back to omega, so to Rn, via the map U. Okay, I get this object. Okay, so this is a one form, a regular one form, right? So this is from Rn to it eats a vector field and gives you a real number point by point. Okay, a standard one form, such that this property holds. This is very important to keep in mind to have an intuition of what the Jacobian does. Let me write it here, so that if you have a map that lifts in W11, and this need not be the case. Okay, so not every map in W11 can be written like so. Okay, this is very important in this business. Then the Jacobian of U, if you want the whatever, okay, identifying forms with vector field is the gradient of the phase. So the Jacobian is the one form that is the differential of the phase, but is defined always from the map U, even when U admits no lift. Even when you cannot write U as a map like so. So, by duality, you can define these. You can take another differential in the sense of distribution of little ju. Okay. This is called the Jacobian n-2 current. Is a well-defined distributional two form, right? So you can really imagine that in Rn you can expand the Jacobian as a two form. Just the coefficients are distributions, so they can be concentrated on singular, on lower dimensional objects. And to this object we associate an n-2 current. So this formula is basically a tautology. So there is a canonical way to identify distributional two forms with n-2 currents, which is the sort of the identity up to the Hodge dual. So don't think too hard about this, because if one unwraps the definition, this is it's nothing basically. If you integrate this with n-2 currents with the Hodge dual, you get this. Okay. And this is called the Jacobian 2 current. So it's important. This is not necessarily an integral current, okay, but it will be for us in most cases. Okay, now I will tell you some examples of what this measure, which is an n-2 current, does, okay, for some maps. So first, star Ju, the Jacobian of U, measures the n-2 dimensional vortex charges of U. So you can think that this current is essentially zero, okay? So I think it's useful to keep in mind the following, that if U is smooth, I'm not sure if this is misleading or no, okay, it's fine. Then star Ju is du1 wedge du2. Okay, so this is really the Jacobian in the sense of determinant. Okay, but now the point is, where U is smooth and S1 valued, these two guys are parallel, okay, and so this is zero. So the Jacobian, in some sense, is detecting the singularities of U, but is only detecting the n-2 dimensional singularities of U. Okay. In the following sense, so that if you take the example that is more or less the case n equals 3 there, so if I have a map U, okay, no, I said picture 1 again. Okay, if we look at picture 1 again, so if I take a map U that is smooth everywhere and has degree D around an n-2 dimensional object, okay, the Jacobian of U is the degree around sigma times sigma in some sense. So sigma considered as a current. Okay. Maybe a slightly less trivial example, but that is important for us today, is if you take n equals 2, so we're in the plane, picture 2. If I take n equals 2 and the map U, which is in W11 from a two-dimensional disk to S1, so the n-2 dimensional singularities of U are points, okay? But the point I want to make here is that the Jacobian, so will be a sum of delta, but you can have infinitely many deltas, okay? So the picture will be something like this. You have D1, the two-dimensional disk, and I will have a sum of things that have either degree plus 1, okay, plus something, but let me assume that, so in my notation here, that the 1 over pi, the Jacobian of U, is a sum of delta. Here the points are not necessarily distinct, okay? And I use this to say that also the Jacobian is a boundary of a current with finite mass, okay, but whatever. So you will have some degrees, plus and minus, maybe, okay, we can put minus 10 degree here, plus 9 here, whatever, but the point is that you can have clustering dipoles, okay, for a map in W11. So the sum here can be infinite. Okay, the Jacobian can have infinite mass in W11. Okay, let me briefly speak about the known results on this problem. So fix a P between 1 and 2, and we'll send P to 2, okay? And a map G in W11 from the boundary of a domain to S1. And assume I'm given P energy minimizing maps in omega. So I minimize the energy with prescribed boundary datum G, for which this condition holds. So actually, this condition is implied by being P energy minimizing, but in general, this is the natural energy condition for sequences to treat, for example, gamma convergence and so on. So if you assume this, there is a result by, so this result, I'm sure some people knew, but it's very hard to find. So this is cited in a survey paper of Lin that tells that this was a result by Hardt and Lin that was never published, but then I found papers that refer to this result as if it was known. So, okay, but assume it is known. It's somewhere. Okay. As p tends to as p tends to 2 and up to subsequences, the normalized energy densities, so 2 minus p times the gradient of up to the p over pi, okay, converge in duality with C0 to a limit measure. Okay, the fact that they converge to a limit measure is just that this has bounded mass, okay, by my energy bound condition. Oh, also this is important. I will refer to this energy condition as the energy bound for the entire talk, okay. Then the measures converge to a limit, and the important part is the structure of this limit. So the support of the limit is equal to the support of a current, okay? And the mass of the limit measure is the mass of a current, where T is the area minimizing n-2 current with boundary, the Jacobian of G at the boundary. Okay, so the vortex charges of G at the boundary. Now again, here there is a catch. So I think the result as stated in Lin's paper is slightly imprecise because it's not true that T minimizes the area among all integral n-2 currents with this condition. But at the end, I will speak very well about why. So by the way, I'm sure that in the proof, this is what they obtain. Just that if you read the statement on the survey, I think it's not true that the area that T is area minimizing among all currents. Okay, this. Okay, so this is the first result, which is for P energy minimizing map is exactly a formalization of this idea that the limit map connects the vortex charges of G with minimal energy, right, with minimal area. So there is something known about the convergence of critical points. So fix P between 1 and 2, and M a closed manifold. Okay, you can even do this with prescribed boundary datum, but the paper I will cite here is for closed manifolds, so take it this way. And consider a sequence of W1P maps from M to S1 that are stationary. Stationary just mean critical points with respect to inner variations, okay? Stationary P harmonic map for which the energy bound, this one, holds as P tends to 2, okay? Then there is this paper by Daniel Stern that tells you the following, that as P tends to 2, the same normalized energy measures converge in duality with C0 to a limit measure that is, has a structure that is less simple than the one before of minimizers for various reasons. So first, the limit measure can have a diffuse part, okay? So this part is not supported on an n-2 dimensional set. Okay, so this is generally like a smooth function times the volume form of M. Okay, but even if you disregard this is a pathology of the method in some say, but I'm sure there are ways to make sure that this does not happen. The limit n-2 something is a varifold. Okay, so the limit measure is a stationary variable, so a weak minimal surface with mean curvature equal to 0 in a weak sense, okay? n-2 dimensional and rectifiable, and the support of this guy is the limit of the singular sets in Hausdorff distance. But note that, and this will be key, I'm not saying that the varifold is integral, okay, at this point. So this is a stationary variable, n-2 rectifiable, but I'm not saying it has an integer multiplicity. Okay. And actually, it is not known up to now. Okay, so these were basically everything known about this kind of convergence on this, for this. And our result, in our result, we established the full gamma convergence of this functional, which means if I take a sequence of maps that satisfies the energy bound as P tends to 2, then two things holds. So first, the compactness and gamma lim. So there is an integral n-2 current such that the Jacobians of U converge to T in the flat topology. Okay. and that the mass of the flat limit bounds from below the limit of the energy. Okay, and then we also have the Gamma-Lin soup, which is just to say for every fixed current like this, you can find a sequence that saturates the inequality above. And actually, we have the same statement in every codimension. So this is the statement for codimension 2, and guys with values in S1. But if you read our result, is for mass with values in k-dimensional spheres for any k greater or equal than 2 and p tends to k. Okay, just that here I focus on codimension 2. Okay, so some comments on our result. Okay, let me check the time. Not too bad. Okay, some comments are the following. First, in general, the map themselves, UP, do not converge in any reasonable sense. I mean, stronger than they have modulus 1, and so they induce a uniformly bounded sequence in L1 star, okay, and this gives you something, but it could be a random map, a constant map, or this is meaningless from the point of geometry. So the limit current, so the limit of the Jacobian is not the Jacobian of any limit map. Okay, at least in the setting of gamma convergence. So note that here we are not assuming anything on the maps apart from the energy bound. I'm not assuming minimizers, critical points, or whatever. So in this generality, there is no limit map. Okay. And actually, this is typical of the gamma convergence setting. It's the same for the Ginzburg-Landau, for the gamma convergence of Ginzburg-Landau. So this is not something special about our setting. So a second very important point is that we have an identical statement for sequences with fixed boundary datum. So with the correct energy bound, but with fixed boundary datum. Okay. And actually, if this is the case, if I put myself in the setting of a sequence with fixed boundary datum G at the boundary, the limit n-2 current is area minimizing, and this is the correct statement in Hardt and Lin result, among all rectifiable n-2 currents in a suitable cobordism class depending on G. I think that I will explain what this means just with the picture, because I mean, it's fancy wording, but the point I'm making here is very simple, actually. So imagine that you have a torus, okay, but a full torus. So like this is an S1 times a two-dimensional disk. Okay, so I have a torus that is full. So let me prescribe the following boundary datum. So on the bound, let me call this T. This is picture 3. So on the boundary of T, I prescribe a map G that has just two vortices. Okay, so plus and minus. Okay. So, and you'd be like, okay, whatever the limit current is minimizing, that better be this straight segment, right? But this is actually not the case for the following reason, because this is not a problem of prescribed Jacobians. So I'm not just prescribing the Jacobians of the map, I'm prescribing the full map at the boundary. Okay. So if you take these two different scenarios, so now I will tell you two different boundary maps. So, okay, let me consider U1, which is a map from the torus to S1. Okay, so U map is a map from the interior to S1 that has as a singular set just this segment. Okay, let me call this one. So this, you have a vortex here, right? And then I just define G1 to be U1 restricted to the boundary. Okay. Now instead consider U2 that goes from the torus to S1 and define G2 as U2 restricted to the boundary. Now the point I want to make is the following, is that these two boundary datums, G1 and G2, have the same vortices, okay, so have the same Jacobian at the boundary, but they behave differently on the whole torus. So for example, the G1, the one given by the trace of the map with this singular set, has degree 1 on circles that go around this vortice, but has degree 0 on these circles, right? And G2 does the opposite. Okay. G2, the trace of the map that has singular set this, has degree 1 on this circle because this encloses the vorticity set, but has degree 0 there. Okay. And the point is, if you do the minimizing procedure and then pass to the limit with G2, you will not get the straight segment for topological reasons, okay? But you will get this current. Okay. So the current is area minimizing in a coordinate class, whatever. The point is not just the area minimizing current that connects, the minimal that connects the two vortices. It depends, maybe you prescribe some useless degree of the map in another place that forces your current to pass there. Okay. Okay, so from the state, so we have a statement for prescribed boundary datum, and since gamma convergence implies convergence with minimizers, so for example, with prescribed boundary datum, from our result, it follows very easily the result by Hardt and Lin, okay, where the limit measure is the total variation of the limit current of the Jacobians. Okay. So now I wanted to compare our result very briefly with other codimension 2 models. So our result is for the P energy, is completely analogous. If you read the statement, is identical. Is completely analogous to the result by Alberti, Baldo, and Orlandi, which is a very famous paper in this business for the Ginzburg-Landau energy. Okay, for sequences that had the correct energy bound. And actually, very recently, the same gamma convergence property in codimension 2 has been proved by Parise, Pigatti, and Stern for the Yang-Mills-Higgs functional. Okay, which I don't want to go into the details of this, also because I don't know them very well. Okay, but it's a model for it's a diffuse model for minimal surfaces in codimension 2 that, for many reasons, is the correct parallel of the Allen-Kahn equation instead of the Ginzburg-Landau functional. If you're interested, I can tell you more about this analogy. I'm not sure I will have time. Okay, so just to here, U is a map that is from, let's say, from Rn to R2, and A is a one form or a vector field. Okay, and in the Yang-Mills-Higgs framework, one minimizes or deal with sequences that are couples of map and one form. Okay, so in the Yang-Mills-Higgs framework, there is a two-form associated with the couple UA that is called the gauge invariant Jacobian, and I will not define it. The point I want to make is just the following, that whatever this object is, which is the parallel of the Jacobian, okay, one can prove very easily the following pointwise estimate. So the Jacobian, which is identified with an n-2 current, but as you see here, at least for smooth object, it's a wedge of derivatives, okay, right? It can be bounded pointwise from above by the energy densities. Okay? So in the Yang-Mills-Higgs framework, so by hypothesis, if I take a sequence U epsilon, A epsilon, the Jacobian have bounded mass. So in the result by Parise, Pigatti, and Stern, the non-trivial part is not that a subsequence of the Jacobians converges, which is something that in our setting is already difficult. The challenge, their compactness result in the gamma convergence, is that the limit is an integral current. Okay, the extraction of a subsequence is almost trivial. The point in their paper is that the limit is integral. Okay. Now, for the Ginzburg-Landau framework, it is not exactly the same, but still very similar, because the pointwise, the Jacobian, which is this object, du1 wedge du2, is bounded by du squared. Okay, and so if I start with the sequence for Ginzburg-Landau with the standard energy growth, it is not true that the Jacobians of the maps are equibounded in mass, but their mass diverge very slowly, okay, as epsilon tends to 0. And this is crucial in the argument by Alberti, Baldo, and Orlandi to prove the gamma convergence. And the basic idea is very similar to what we do. This part is I would say, standard for experts. So you deform the Jacobians to a current that is an integral polyhedral boundary supported on a grid. Okay, this is the Federer-Fleming polyhedral deformation, more or less, at a diffuse level. And then they can prove that the mass of these deformations is bounded by the energy over log epsilon, which is less than a constant. Okay. From here, the compactness and integrality of the limit follows from the Federer-Fleming's theorem. Okay, so why I told you all this business about the mass of the Jacobians? Because in our setting, one big difference between our setting and other models is that we have no control on the mass of the Jacobians, so, which are supported on n-2 dimensional sets, but might have infinite mass, even for fixed p. So if you look at picture 2 again, in 2 dimensions, where the mass of the Jacobian is the number of points, I can have infinitely many for each fixed b. Okay, so the setting here is different because I have no control over the mass of the Jacobian a priori. Okay, so for every p, the mass of the Jacobians could be infinite, and you have to deal with this, okay, in some way. And indeed, one of the key steps in our proof is that we start from a sequence UP with the energy bound, okay, with the correct energy bound for the gamma convergence, and we deform this sequence to a new sequence, okay, that is moved outside an n-2 dimensional surface, such that, but maybe I can even not go into the details of the, such that some properties hold. I will just point to the second one. So we can deform the Jacobians in a way that the flat limit is the same, but the mass of the Jacobians exploded most polynomially. Okay. So from here, once the case n equals 2 is done, one can closely follow the deformation into grids argument by Alberti, Baldo, and Orlandi. Okay, which again, this, I think that for us, it wasn't necessarily the easiest part, but for expert is probably the easiest part. I'm just saying that there is a way to slice the currents and then use the two-dimensional result, that if you can do the gamma convergence in 2 dimensions, you can do the gamma convergence in every dimension by deforming the Jacobians into grids. We can deform the Jacobian on n-2 dimensional grids. So the Jacobians are one current. So in R3, a very vague picture is that you can think like this. You have a one grid, a union of cube. You can deform the Jacobians to be supported only on the grid, okay? So that you are close to the starting ones in the flat topology, because if not, this deformation is useless. And such that the mass can be estimated by the restriction of the maps UP to the dual two-dimensional grid. So to the union of the two-dimensional planes that passes through the midpoints. Okay. And so if you know the result on these two-dimensional planes, up to projecting on grids and deformation, not to say that this procedure is easy. I'm just saying that the main novelty of our work I think, is the proof for the case n equals 2. And then if you gave this object to an expert, I mean, we followed very closely the argument by Alberti, Baldo, and Orlandi, but which is also what Parisi, Pigatti, and Stern, I mean, in this business, people know how to do afterwards, okay, with this deformation into grids. The main novelty of our work is the proof of the case n equals 2, or actually n equals k in general, which is the following result. So focus on n equals 2 and take a UP, a W1P map from the disk to S1 with an energy bound. Okay, so you can think this picture, so a fog of points that as p tends to 2 is moving. Okay, we know that the Jacobian is a sum of delta, but it can be infinite. Exactly. Okay, since in general the mass of the Jacobian is infinite, at the end of the day, the whole point of the proof reduces to the following. So you have to find the decomposition of the Jacobians. So again, the Jacobians are fog of points. So this result is very concrete. Like you could explain the proof to first year undergraduate students. So you have a fog of points, plus, minus, and they can have degree attached, and they are moving into the disk of radius 1. And they are infinitely many for every p, okay? And you have to split this in two families, one that they call the mass part and the flat part, such that as p tends to 2, with the energy bound, the mass part is uniformly bounded, so a bunch of the points are bounded in number, okay, up to throwing away a tail that converges flat to 0. Okay. So if I can do this, then the compactness and integrality of the limit, everything else was known. Okay. So the point is really to declare a recipe that is elementary, not easy in my view, but is to declare a recipe to do this. So I give you a fog of points with degrees and stuff, and then you have to find a decomposition that do this. Okay. And in our paper, we found a way to do this that is, I think that it's very nice, but I have to say that it's very particular to the sphere-valued case. So people asked us if we could treat general manifolds with some topology in the target, but our method, I think, is very clean, but is very particular to this case. So we use the Coera formula and everything. So it's very particular for spheres. So a few words about future directions, and then I'm done. So in the paper by Daniel Stern, the one I cited before about the convergence of critical points, he finds a stationary variable that is n-2 rectifiable with density bounded below by 1, okay, on its support. So, but actually, he does not prove that the density is always integral. Okay. He does not find an integral varifold as a limit. So the question would be, is the density of the limits as varifolds? Because for us, so this is an important point to make. If you take the limit of the Jacobian in the flat topology, okay, or in the gamma convergence setting for minimizers, so you are allowing for all the cancellations that you want, right? Because the flat topology is canceling opposite vortices. So, and in doing so, we obtain an integral current. Okay, so if you treat minimizers, or you take the convergence in the flat topology, so you allow for every cancellation possible, and what's left is the gamma limit, what has to be left, right? Not for the result to be false. And this is one thing. But if you take the limit of the energy densities as varifolds, you are counting the area with multiplicity every time, even plus and minus. So it is not trivial, so given in any sense, that in this case, the limit varifold is integral. And actually, don't be fooled by the codimension 1 case, because Actually, for the Ginzburg-Landau functional, in a very recent paper, okay, no, nowadays not very recent, in a recent paper by Alessandro Pigatti and Daniel Stern, they prove that for the Ginzburg-Landau functional, this is not the case. So the limit varifold can have density that is almost arbitrary. It's quantized just between 1 and 2. If you are within 1 and 2, you are 1. If you are less or between 1 and 2, you are 1. But you can realize every density in 1 union 2 plus infinity. Okay. And even with sequences, so this is not something about that the limit is supported on a bad set. They construct such sequences where the Ginzburg-Landau energy density concentrates on an n-2 dimensional affine subspace. So in R3, they build sequences that concentrate on a line with basically arbitrary density. Okay. So in this business of codimension 2, the integrality of the varifold is not given. Actually, it's not even clear to me if after this result, the community believes that for the p-energy version, the answer to this question is affirmative or negative. Okay. So there are no counterexamples, but I don't know. Okay. And I think I'm up with time, so thank you for the attention.